In today's session, what we are going to do is we are going to start the data cleaning where we left, and we are going to talk about different stuff. Now, the first thing that we are going to understand is the categorical variable. Okay, categorical variables are the variables where we have some kind of names or some data with text. If we take a look at this particular data, the department is a categorical column. Like we have names for different sectors. Name is a categorical column. Like we have different names that don't have any numeric significance, but today we are going to learn that how we can use them in numerical computation. Like whenever we are working with any kind of machine learning model or data science, we need numbers because most of the models are basically nothing but formulas of some complex mathematics, and we need to give some numbers to that particular formulas to generate results. Okay, so today's session will be revolved around categorical variables and little bit of scaling and standardization. We will talk about them when we go to that topic. Okay. Now in categorical variables we have nominal and ordinal, two different types of categorical variables, and we treat both of them in different ways, right? The main point, what is the main point of treating them? The main point of treating them is we need numbers instead of text. Okay. Now, nominal are the variables. Let's start off with the nominal. Now, nominal are the categorical variables where order doesn't matter, right? Like if we want to see some kind of examples, different colors like red, green, blue, there is no superiority or inferiority. Like we cannot say that green is going to be better than red or something like that. In the same manner, gender is also a nominal variable. So basically, the main difference between nominal and ordinal is the nominal don't have any specific order, and in the ordinal variables, we got specific order, right? In nominal, we don't define that this particular category is superior to this particular category. But whenever we're talking about ordinal categorical variable, we can define that, right? Like if we have something like this rating, poor, good, excellent. Now it makes 100% sense that excellent is better than good and good is better than poor and excellent is better than both of them. So this is what I'm saying order here. So we
Yeah,
have
what about education? Is it ordinal or nominal?
it's ordinal as well. We have an order, like nobody can do a master degree before high school degree, right? So they go through high school, then he will go through bachelor's, and then he will move on to masters. So we have specific order. Master's degree is always going to be superior than a high school degree or bachelor degree, right?
Oh, yes.
Do you have any kind of confusion? Please ask.
No, I don't have.
Cool. Now, we are going to convert these columns into numbers, and we are going to make sure that these columns are in the makes perfect sense. For example, to treat these columns, category nominal and ordinal columns, we have two different types of encoding styles. Encoding basically means converting text into numbers. The first one we have label encoding, and the second one we have one hot encoding. Now, in label encoding, we basically talk about ordinal variables. If we have order, we will go with the label encoding. If we don't have any order, we will go with one hot encoding. So this method is designed for nominal categorical variables, and this is designed for ordinal variables. Now, what we are going to see that what basically we are going to do to in one hot encoding and label encoding. Now, if we have a columns like this in our data set, it means they are categorical column. And now we need to specify that either it's an ordinal or nominal. Now, in the colors, we don't have any specific orders. In the same manner, in car brands, we don't have any specific orders. Like we can expect expensive car from Toyota as well, and we cannot distinguish that this particular brand is going to be much better than this one, right? It mostly depends on personal preference. Some people have blue favorite color, someone have green, so we cannot just say that blue is always going to be superior than green or something like that. Now, if we're talking about ordinal columns, we have something like if we are talking about clothing and there are sizes like small, medium, large, extra large, they are going to be ordinal. Like this makes perfect sense. Like small is always going to be shorter than medium or large or XL, right? In the same manner, we can have higher education columns, rating columns. All these columns are basically what we call ordinal categorical variables. They contain text. The text have specific orders. And if we give them specific order, that makes perfectly sense. Now let's talk about what is label encoding. Now, the main goal of discussing all that stuff is to convert these text into numbers, because for any kind of model we need numbers so we can put them and use them as a standard column or standard variable. Label encoding is simple. No matter how many categories we have, we will just assign a number to each category. We will say this particular category is 1, this is 2, this is 3, this is 4, and like that. Now, since we are dealing with numbers, and since we are dealing it in some specific formulas or in specific model, if we say that like 1 and 3, like it's thrice the 1, right? And we cannot use them as an equivalent in our data, right? So that's why we can only use label encoding when we are talking about ordinal variables, like when we do have order. It does, if I am specifying that 0 is for uneducated person and 1 is for high school and 2 is for bachelor degree and 3 is for master degree, that makes sense. Like this master degree person is basically more educated than all these categories, so that's why he got a higher number, right? In the same manner, if we are talking about different clothing sizes like small, medium, large, we can say that the third one is basically the bigger size than 2 or 1 or 0. So that's basically what we call label encoding. Now, label encoding is simple form and it doesn't increase the data much. If you already got 10 columns and you are converting it with label encoding, you will still have 10 columns. But instead of categories, now you will got some numbers here. Like if we have education column and we have high school, bachelor degree, master degree, PhD, and all that stuff, what we just did is we just created a new column with the name education encoded or any kind of name that you want. Okay, and we just give the categories a particular number. And how we will do that encoding? That's simple. We will just define a dictionary. In dictionary, for each category we will just assign it a number. And once we are done with defining that, all we need to do is we need to use map function. Now, in that particular code, this is the name of our data that we are working on. If we are working on something else, we will just define the name of the data and the column. Now, this column is basically the column that we are going to create. Okay. And here we specified education encoded. Like if you are trying to, if you are working on something else like clothing sizes and you want something else, so you can just remove it to size and the name of the new column will be size or something like that. Okay. And this is the previous column that we are working with, the education column that contains actual categories. And we are using .map function. In map function, we're basically telling the Python is telling that map these actual values to these new values that we just defined. Okay. And once we do that, we will see that in our data set, we created a new column with new values based on our previous column. Now, this is what we call label encoding. We create one column from one column and where order matters, so we can use numbers. Like if order doesn't matter, like for example, if the column that we are working on contains different colors, blue, green, red, or something like that, and we are giving red number 3 and we are giving blue number 0, so whenever we put this particular column in any formula, in any model, we are specifying that green is 3 times better than blue. Sorry, red is 3 times better than blue. Okay. So that's why when we don't have any order, we should not use label encoding. Now, this was a straightforward approach where we use define a dictionary and we just use map function to do that. Also, we have predefined functions for that in scikit-learn package. If in the start of the script you will say sklearn.preprocessing, this is basically a package scikit learn, and this basically contains a lot of pre-built formulas that so we don't need to code everything from scratch. Okay. And from this particular package, we can import label encoder and one hot encoder, and we can use both of the methods without even specifying dictionaries and all that stuff. Like in that particular case, we defined a proper dictionary, but if we are using a scikit-learn, all we need to do is we need to grab the label encoder from scikit-learn. We need to give it a name, and then we just need to use that label encoder with fit transform and specify that what column we are basically trying to label encode. Now here we created a new column, and to just see the difference between these two, automatic label encoding, we are seeing that high school is getting 1, but bachelor degree is getting 0. So since Python doesn't have any sense about what category is better and what category is less superior, we will see something like that. So we should avoid that, and if we want more control over it, and we should use our own mapping style, this one with dictionaries. Now another example, and this is another example where we can convert ratings like good, excellent, fair into properly label encoded column. Now, the benefits of using label encoding is it preserves order. Like we have specific order and we kept that specific order into new columns, and it makes 100% sense that we are basically coming from this particular direction, right? Secondly, it's memory efficient. Like if we already have one column and we created one new column to explain that. And third is it's simple to implement, and it's reversible, so all we need to do is if we want to get back from this particular state to the previous state, all we need to do is we need to just put the one here, put the poor here, and it will just replace the whole encoding to previous state. Now that's how basically we deal with the ordinal columns where we have proper order and we need to use them in machine learning model. Now we will talk about nominal columns where we don't have specific orders, but we need numbers, and we don't want to add bias into our analysis. Like we don't want to specify some category 4 and some category 1. So to avoid that, all we have another method called one hot encoding. Now, one hot encoding is basically a more aggressive way of dealing with the categorical column. It contains in one hot encoding, like let's talk about an example. Suppose we have colors like red, blue, green, and all that. In one hot encoding, what we will do is we will create a new column for each category. Like if we have a red, we will create a new column red. If we have blue, we will create a new column blue, green, and for all the colors, we will create a new column. And in the column, we will have only two types of values, 0 and 1. Like if we're talking about the red here, it was red, so it's going to be 1, otherwise all it's going to be 0. Like if we something like that. Okay, now we have a column with values like red, blue, green. What we are going to do is we will create a column for each of the category. This is for color blue, this is for color green, this is for color red, for color yellow here. Okay, and here we are specifying 0, 1, and the numbers. So basically whenever we in some specific rows, like if we're talking about the first row, we have red here, so the red one is going to be 1 and all the other columns are going to be 0. And in the second column we have blue, so blue one is going to be 1 and all the other columns will be 0. We are preserving that the actual content of our data, and we are making sure that no rating or more scores than the other column. In the same manner, like we did with the label encoding that we imported from sklearn, we can also use sklearn for one hot encoder. Like from sklearn processing, import one hot encoder. Now we imported our function that is needed. All we need to do is we need to use one hot encoder, and we need to define that we are going to save this particular encoder into our new name, and that particular new name is going to be used with the fit transform. Now if we look at this particular code and this particular code, it's totally the same thing, but we are using label encoder here, and on that particular option we are using one hot encoder. We define a label, we define an encoder, we save the encoder in some specific name, we use fit transform on it. And in fit transform, we provide the name of our column that we're working on. And this is basically the new name of the new column in the same data set. Okay. And there's also a simpler way that we can also use is in pandas. We imported pandas at the initial, like import pandas as PD. And this we can also use a function get dummies. Now get dummy function do the same in works in the same style where what we are going to do is we are just providing the name of the column, name of the data that this particular data we are working on right now, and this particular column we are talking about. Okay. And prefix is color. Prefix is basically the word that is going to be at the start of the every column. Okay. If you don't want to define it, you can just use space here and it will be removed. Okay. Now what this will go is this will create the dummies. Now in the get dummies function, create the dummies in binary style. So instead of 1 0, it will show you true and false. Okay, false basically represents 0 and true basically represent 1. In some cases, binary classification can be added in our data formulas. Like we can use this particular data directly into any mathematical formula. Python will know that if it's false, it's going to be 0, and if it's true, it's going to be 1. But for some cases, it doesn't work, and from here we need to use again replace function with false to 0 and true to 1. Replace function that we used in the previous session. Okay. But if we are going with the one hot encoder, all we need to do is we need to import the one hot encoder, and we need to use that with the fit transform, and it will transform the data into something like that. And also, if we are worried about the name, we can, in pandas, we can give the prefix predefined like something like that. But in sklearn one hot encoder, we will go with something like that. We will use f string, like it should start with the with color and dash. After that, it should have the category that we are going to get from our categorical variable. Like if we are going to get different colors, then it should know that the first category is going to be blue and second is going to be green, and it will adopt the same style. At the end, we use pd.concate. Pd.concate basically combine two data frames into a single data frame. Like here, we used one hot encoder. One hot encoder will create all these columns. To make sense of all these columns, we give it a f string with the name color underscore. So whatever the name it's going to give it to the category, at the start of it, we should have color underscore. After that, the data that we generated, this particular data, these columns, we will define that we need it to in proper data format. That's why we're using function from pandas data frame. Okay. And in data frame, we are saying that what data we are going to talk about. We're talking about color encoded that we get from the fit transform. And we are saying that the column's name should be in this style instead of the actual that one hot encoder defined. Right? And so these are the two parameters in the data frame, the name of the data and the columns that names that we are going to use. Now we have a clean data with the name color encoded df. Now what we need to do is we can combine this particular data with the car ID or with the whole previous data set if we want to. In that case, if we want to combine this with the car ID and get this particular data in the clean format, we need to do is pd.concate. Now it knows that I am using a function from pandas, and the main thing that I need to do is to combine two data frames. And in two data frames, we are specifying the first data is going to be the car ID column from car data, and the second is going to be the color encoded df that we just created with the one hot encoding. Got it? And access is equal to 1. Basically, we are specifying that we need to merge them column wise.
Can you explain it again?
This particular point or the whole
Yes.
code?
No, only x equal to 1.
Okay. So whenever we are trying to combine two things, we can either combine them column wise or we can combine them row wise. Okay. Like if we have three columns and we want to combine other three columns with them, we can either like So we have three columns, right? And we have another three columns here. And we want to combine these two. If we got two options, xs is equal to 1 or 0. Xs is equal to 0 means we are going to combine them row wise. So the end data will look something like this. We will still have three columns, but more rows.
Okay.
Okay. And when we're talking about xs is equal to 1, we are basically talking about combining them vertically. So our whole data will become something like this. Okay. And in that particular case, we want to see the car ID with the colors. So we need this kind of concation, not the vertical one, right? Did you got the point?
Yes.
That's why we're using x is equal to 1. Again, we did some examples that how we can use them for different columns. Like if we have countries, we can use this. So we can use again one hot encoding with get dummies or with one hot encoder. At the end of the label encoding and one hot encoding debate, we have a little bit of comparison. The label encoding is for ordinal variable, one hot encoding is for nominal variables. Now it creates a single new columns. One hot encoding creates multiple columns. It label encoding is less memory use has less memory uses because we are creating only one column, but in one hot encoding we are creating so many columns, right? And also make sure when you have a column that has so many categories, you should not consider that. Like if we have a column with the names and we have a data for 10,000 people and there are 10,000 names, and we don't need to treat that. Like we don't need one hot encoding for that. We will just remove that particular column. Like if we create a new column for each name, we are just adding 10,000 columns in our data set and it will become a mess, right? So we will avoid whenever we are working with the categorical column with so many categories, we will just avoid working with it. We will not use any kind of encoding and we will most probably remove that column.
Okay.
Okay. No,
Yes.
one hot encoding have memory issues. Like if we have so many categories, it will create so many columns, and the whole analysis become like, for example, if we are working on this particular data set, we have one, two, three, four, five, six columns total, but we have eight names or seven names. We are adding more names than the actual data set. Now, when we put them into the analysis is based on the names because this become noise, this becomes very less as compared to the names, and the whole point of analysis is to get the idea based on age, gender, department, salary, but this will make no sense, right? Also, it keeps label encoding keeps the order, but in one hot encoding we don't need an order, we are free to that. Here in label encoding we have a risk, we can make a mistake. If we get the order wrong, we are going to make our results wrong, or we are going to create a faulty model that should not be relied on for any kind of analysis or results. Here are some dummy data set that you can use to encode them as you want. And also, these are solved, so you will get the solution at the end as well. Another thing that was problematic in any kind of data is feature scaling and pre-processing. Okay, so now we treated the problems with the categorical columns, like what we need to do about them. Another thing that can be problematic in our data set is the scale of different columns. Like we know we are going to use these numbers into some formulas, right? To create predictions or something like that. Now, if we are adding salary and age in the same formula, and age is such a high, salary is such a higher number, and age is such a small number, this will cause the problem. This will introduce a bias or an error in our analysis, right? So it thinks that salary is much more superior column than the age column, but in reality they are two different things. We have two different perspectives. Like age cannot be that much higher and salary cannot be that less in numbers, right? Now, we need to create a scale for both of them so that our model or our equation or our formula assume that these two columns are quite similar looking, right? That's where we have things like feature scaling. Now, in feature scaling, we will talk about few things. We will talk about binarization, standardization, normalization, and robust scaling. Now, standardization, normalization, and robust scaling are basically related to feature scaling, and binarization is not actually related to them, but it makes some sense when we talk about it. As name suggests, binarization, it will basically convert any numeric column into binary like 0 and 1. Okay. And when we use that, whenever we need to create a new column based on our previous columns, like we have this particular data, right? And we want to talk about only senior citizens, or we need to talk about only young peoples. Now, for that particular reason, what we need to do is we need to create a new column in our data set that identify that either some specific entry is related to senior person or not. Okay, that's what we call binarization. Like we convert a numeric column into a new column with the name that contains only 0 and 1. Like if we're talking about the senior citizens, what we need to do is we need to convert the values. We need to find a threshold like this particular age, like if we say 45 or say 50, above 50 we will give them senior status, and under that they will not be considered as seniors. So what we need is a threshold value that we define on our own based on the knowledge that we got. Okay. And what we're going to talk about, we will care about below this or above this. Like if you're talking about senior citizens, it doesn't make any difference if we're talking about someone with the age of 25 or we are talking with someone with the age of 45, because we are not considering them seniors, and we will consider only senior when someone is like, let's say, above 55 years old. Okay. So we are basically creating flag or indicators. In the same manner, we can create indicators for high and low income status, pass and fails in scores, and different things. Like for example, if we're talking about age and we are saying age greater than or equal to 60, if we have age greater than that, we will give a value 1 in the new column, otherwise we will give 0, right? Now, this is basically called binarization. So we can create a binary column, and based on that, we can do analysis in our data set in the next steps. Now, we created this particular data, we give it a name scaling data, and whenever we are starting working on it, we will just create a fresh copy and we will work on the copy. Now we're getting few columns: is senior, got high salary, experienced, high score. Now what we're going to do is we're just going to define a condition, and based on that condition it will assign the values. Now this is our name of the data, right? Now when we write this, we are basically telling him that we are talking about this particular data, and when we write this, we are basically telling him that in this particular data we are talking about the age, and we're defining a condition that age should be greater than 40. Now when we run these lines, it will create something like that: if it's greater than 40, it's true, otherwise false. Okay. And what we need to do is we need to put another condition dot as type integer. So when we convert its type to integer, instead of true or false, we will get numbers. Like if, all right. In the same manner, we can do the same thing with salary, experience, score, and all that. All we need to do is what we need to do is we just need to define the conditions, and we need to convert the true and false into specific category into integers. Like if I run these lines of code, and if I, for example, remove that thing from here and run this, now you will see that we are getting true and false, right? And these true and false are basically based on that particular condition. If it's greater than 40, it's going to be true, otherwise it's going to be false. Like here we have age 45 and we are defining threshold of 40, that's why it's true. And
Okay.
when we type dot as type integer, it will convert this into 0 and 1. And
Okay.
we did the same stuff with all the columns. This is called binarization. Again, this is a manual way of doing things. We have a proper function for that. Binarizer in sklearn processing, what we need to do is we need to just give it a threshold value, and based on threshold value, we can use fit transform. And again, the same style, same context. So whatever we're using from sklearn.preprocessing, it's most probably going to use the same style. We will define our function, we will save it, and we will use it with the fit transform. Now, these both things are going to be the same thing. Now, let's talk about the other part of our analysis. Now, another thing that we have is standardization. Standardization, there are two terms in statistics. One is mean that we call average, and one is standard deviation that we call spread, right? So what we're going to do is we are going to make the mean of our data is equal to 0 and standard deviation is equal to 1. Okay. So we will take the age column, and whatever its average is going to be, we are not concerned about that. We will going to map that particular average mean to 0. Okay. And based on that, we will create two new columns for age and salary that will scale them, so they both look quite similar but still have the same meaning behind that. Now, if we talk about the formula, that how scaling is done, standardization is done with the z-score. Now, z-score, basically this formula is what we call z-score. it, this z is basically the scaled value that we got at the end. X are the actual values in our column. Like if we're talking about the age, the actual value is like 20, 25, 30, 35. This is what X is. New here is the mean of the features that we get. Sigmoid function basically here represents standard deviation for the features. Okay, so what we are going to do is we are going to pass our data through this formula. We take the mean of age, we take the standard deviation of age, and we put everything in this, right? For the first value, for the second value, for the third value, and based on that, we will create a new column. And that new column is called standardized version of that particular column. Okay. Now, when to use standardization? When we have different scales, like age is such a small category, such numeric column, and salary is such a higher column, so we need to map them on same. Okay, and algorithm assumes normally distributed data. Uh, do you have any idea about normally distributed data?
I heard, but I don't quite remember now.
No problem, no problem. So normally distributed data is basically when data is in bell shape. Let me
Okay.
find some map for this. This is what basically normal distribution data look like. If we talk about the age, for example, if we talk about the age, there are so many people in from their 20s to 40s, but there are quite less people at the higher ages because death rate increase with the age. In the same manner, death rate is quite higher when a kid is born, and that's why we see a lot of people between these, like some, if a baby is born and he's totally fine, then there is a lot of high probability that he is going to make his age like 30, 35. But after that, we all go through problems, and that's what basically normal data look like. Do you understand the point?
Yes.
Apart from that, if we talk about something else like height, like most of the people's height is between 5.5 to 5.9 or something like that. There are some people, very few people with less than five height of 5 feet, and very few people with the height of more than 7. So basically most of the data lies between in the middle, and few data at the higher end and at the lower end. That's basically what. So now, if we are talking about using mean as 0 and standard deviation as 1, it means our data is in this particular form. If it's not in this particular form, we basically cannot implement that. Even if we implement that, the scale is not going to make much sense to the algorithms or to the models. Okay, so this is a condition. Like if data looks like this, we are going to use this. Now, in our data set, like we have age, and we know age is normally distributed. Like very few people get to the age of 100 or to the age of 95, right? Now, and salary is also normally distributed. Like most of the people get around the average salary, few people get much higher, and few people get much lower based on the performance or some metrics that they're following, right? So in that particular case, we can use z-scoring. But if we are not talking about something like that, then we need to reconsider our scaling approach and we should not move on with the standardized scaling using z-score. No, features have different scales. That's why we use it. Algorithm assumes normally distributed data. Data should be in the bell-shaped format, and we discussed that. Using algorithm sensitive to scale. Now, neural networks, different machine learning models are sensitive to scales. Like they are based on mathematical equations, and when we put something like that, a variable with such a higher numbers and such a smaller number in a same equation, they just ignore the effect of this particular small column because they have such a higher numbers here. That's why scaling is important. And also it preserves the shape of the distribution. Like before scaling, your data looks something like that, and after scaling, it will be still the same looking data. No, it preserves the outliers. Like if your data set contains outlier, the outliers still remain in your data set. It centers the data around zero, so no matter what column you're talking about, all the columns are centered around zero. Like we will get smaller numbers instead of such a higher numbers, and works well with the algorithm that assumes normal distribution. Now, some machine learning models assumes that we are working on normal distribution data. Like if we're talking about linear regression assume that our data is normally distributed. Okay, so for these particular algorithms that assume that have assumption of normal distribution, this scoring works perfectly fine. Now, how can we do that in Python? We just created a fresh copy of our data set. We took the mean, we took the standard deviation of our column, and based on that column, we just use this formula: x minus mean divided by standard deviation. X is basically our column minus mean divided by standard deviation. And we created a new column with the name salary standardized manual, like we did it manually. But we can use sklearn.preprocessing, and from here we can use standard scaler that will do quite the same thing. Again, we need to save the scaler and we need to use fit transform on that to scale them. Okay. And here we are doing it for the four different columns like age, salary, experience, and score. So we can just combine all the columns and we can just give it in the name here in fit transform and it will scale all of them. Okay. And again, we are creating a data frame based on the data that we get from standard scaler. We are adding a naming convention with the actual column that names that it contains, like age, salary, and add is standardized with underscore so that the new columns we can distinguish between new columns and the old columns, right? And at the end, we again use pd.concate to merge the complete to get a complete data set, the complete picture. Now, this was our age like 25 here, but after standardization, we get age like minus 1.2. Okay, why? Because it took the mean age and it converted it into zero, and based on that zero, it created the values, right? Now here we have such a higher numbers, but here they are very small numbers that we can directly use in our any kind of machine learning models, and it will not assume that this particular column is superior to this column or something like that. Do you understand the point?
Yes.
Cool. Now let's move forward, and here we just check the mean and standard deviation. That as we know that the z scoring promise that we are going to get mean of 0 and standard deviation of 1, and here we checked it and it's giving the same results. We are getting some minus here because it's going to be minus 0.000 something, and it's almost close to 0, so but it's still getting it in the minus. Okay, now the second method that we're going to talk about is normalization using min-max scaling. Okay. Now here we do the different things. What we do is we take the highest value in our data set. Like for example, if we're talking about the salary and we have the highest salary of 75,000 and we have the least salary of 45,000. So what it's going to do is it's going to give the highest salary a number 1 and the lowest salary in number 0. And it will spread all the other values between them so that they make perfect sense. Okay. And the formula for normalization is X. X is basically the column that we're talking about. Like in that particular case, if we're talking about salary, so it's going to be salary minus minimum salary divided by maximum salary minus minimum salary. So this is basically a mathematical formula that normalizes the values between 0 and 1. You don't need to remember these formulas, not for this one, not for z scoring, because because they are all already coded into Python that we can use. But you should know about the theory behind that. Like if you're going for some kind of interview, so you have better idea about these things. These are the small things that they focus on during the interviews.
Okay.
Okay. Now, the values that we generate from this is what we call normalized value, the new column that we basically generate, right? And for example, let's talk about the data here. And now, whenever we did standardization, we will get minus values as well. Like we are basically centering the data based on 0. We will get some minus values, get some positive values. But whenever we are min-max scaling, we are we are converting the values in the range of 0 and 1, so all the values will be between 0 and 1. There should be no minus values. Like if you are getting minus values here, it means there is some kind of problem in your code, and you need to reconsider the approach, or you need to reconsider the coding style. Okay. Now in the same manner, like in standardization, we go with the mean and standard deviation and then put in the formula. Same we will do here. What we will do, we know that in formula we have minimum, maximum, so we will calculate the minimum, maximum, and then we will create this particular formula. We create a copy, we will find the minimum, we will find the maximum, we save it in the salary minimum, salary maximum, and we use the formula that this particular column minus its minimum divided by maximum minus minimum. And once we run this line of code, it will save and create a new column in normalized data with the name salary normalized manual. Okay. Again, you can create it like that if you want to. You can use the min max scalar as well if you want to. Both are the same thing. It's totally up to us, whatever we prefer. Okay. So once we run that, we will get something like this. We will have normalized columns. We will have all the values between 0 and 1. Now, in Z-scoring, we prefer that our data should be normally distributed. But here we assumes that our data is uniformly distributed. Okay, uniformly distributed means basically each data lies in specific range. Like if we say uniformly distributed data, and we just take a look at some, so this should be look something like this. Okay, in uniform we have a bias that there are very few people at the higher end, or there are very few people at the lower end, but here our frequency should be same across all of these. Do you understand the difference?
Yes.
Perfect. And so whenever we're now, for example, if we're talking about some example for uniform data, like if I throw a dice, it contains numbers from 1 to 6. So there's a probability of 1 as much as the probability of 6, because each of them paired one time, right?
Okay.
And this approach is basically designed for this particular style of data. Like if we have this kind of data, then we go with this one. Otherwise, we will go with the z-scoring. At the end of the day, we have robust scaling. Okay. In robust scaling, what we do is we scale the data based on the IQR range or interquartile range. Okay. No, it's simple. What we do is basically we use median and IQR instead of mean or standard deviation. Like here, we are in the Z scoring, we are using mean and standard deviation, right? Instead of doing that, we will use IQR range and median. So here in this scoring we have mean, but we still here we're going to talk about median, and here we're going to talk about IQR range. Now, what is the IQR range? For example, this might be the valid question, right? When we are working in the previous session, we used a function describe, this one, right? And this gives us the percentile, like 25th percentile, 15th percentile, 75th percentile. The 50th percentile basically is what we call median. And these 25 and 75 are basically the interquartile range that we call IQR. Got it?
Yes.
Perfect. Perfect. So what we're going to do is we're going to use this formula for this robust scaling. Now, when to use robust scaling? When our data set have outliers. If our data set have outliers, then we will go with the robust scaling. Okay. Now, the question should be why we should go with the interquartile range when we have outliers, right?
Okay.
Suppose we have a data set something like this. We have points something like this, and there lies an outlier here. Okay, and we are using z-scoring, and z-scoring is based on the mean value, right? When we take average of all these values, average will lie something here, but this is not true representation of our data set. Our data set lies here. Due to this faulty value, our whole mean is relocated to another position, right? So whenever we have outliers, we will not use z-scoring. Instead, we will use this particular approach, robust scaling. So it uses median instead of mean. So median is not based on the average, but it's based on the 50th percentile, like 50% of the data where does it lies. So we will get median something like this, like there, because most of the data lies here. Do you understand?
Yes.
Perfect. In that particular case, we move on with the robust scaling. Again, the same thing, we are just getting a data set, and instead of finding the mean and standard deviation, we will find the median and quartile range, 25 percentile and 75 percentile. Okay, and we are giving it a name like income Q1, income Q3, and the interquartile range is basically Q3 minus Q1. So basically, if we minus this particular value from this particular value, we get the IQR. After doing that, we will just put it into the formula and get our columns standardized. Okay. Now here's a little bit of comparison that you should go through. Like if I just scale the data based on all three methods, and we just compare the values. Now, if we talk about the
Mm.
comparison between all these methods, we first discuss binarization. In binarization, we are not preserving any distribution, or we are not sensitive to outliers. We are just using a threshold value, and we are using creating two categories, 0 and 1. Okay. In standardization, we are considering the data is normally distributed, and it is best whenever our models are assumes that we need a data scaled. Okay. It is sensitive to outliers because we are using mean, and whenever we use mean, we get problems like this that can cause a problem. So if the outliers are present in the data set, we should not use this particular method. Okay. And it preserves the distribution. Like if it was all bell shaped, it will remain the bell shaped. After that, we talked about the min-max scaler. In min-max scaler, we scale the values between 0 and 1, and not just 0 and 1, but between 0 and 1. So it is very sensitive to outliers. Like again, if there are outliers, it's going to be problematic. Okay. And we work with this when we have uniform distribution, and when we want a bounded features, like we know that this maximum value and its minimum value should be 0 and 1. Okay. After that, we have a median-centric robust approach that we can use if we are considering that we need to preserve our distribution, like our data set should look as it was before, and we want to make sure that the outliers did not affect our analysis. Okay. So based on that, we can understand that what we need to use for different scenarios. It's a small data set that you can go through and use for your analysis. Now, this is a graph that just shows that how basically it affects. Now, this was the income column, and it has these different income groups. Now, the shape of the data remains same, preserved, right, in robust scaling. But the scale get different, like we have smaller numbers instead of all that high numbers. Same with the age. We standardized it with the z-scoring. The shape remains the same, but the numbers get smaller. Okay. And there are small notes, but still they just contain all that stuff. This is the theory on the basically on the outliers that we talked about, that how it's gonna affect the outliers. So that's it for today's session. I think you should go through this, and if you have any question, you can ask me.
Okay, thank you.
The rest of the analysis is going to be the similar.